Hello juniors, let's try and explain you what is analog flow in the simplest way possible. As you can see, there is a whole flow chart starting from the design specification, which comes from the customer, and it has to go through the whole cycle finally until we reach the end of the design. Let's take each of these steps and try and understand how it is done. Okay. Now, the customer comes up with the specification saying that I have a requirement of a PLL, for example, right? He comes up to the designer and says, design this particular thing. So what does the designer do, right? So he has got a team, right? He'll be a designer and he's got a full team of engineers over here, the circuit designers. So assuming that there is a requirement of a PLL over here, you've got different building blocks in a PLL, right? There's a LPF, that's a low pass filter, that is the voltage control oscillator, charge pump, and all of that. So this particular design head has got his team members who are specialists in each of these modules. So he does the design partitioning and gives each of the guys their share of work and gives them the specification saying that, okay, the customer is expecting us to design a PLL at certain gigahertz with certain power requirements and blah, blah, and all of that. So each of these guys take up their share of work. So assume then, please note that this is a whole teamwork. It's not one man's job. So all of the designers who are specialists in each of their genres pick up their share of work. And then they design each of their modules, okay, with their own specification. So that's how the design partitioning is done, and that's how the job is divided. So next. So the first stage here is, so after we finish the design partitioning, it's the schematic design. So this mainly we also call them as a circuit designer. So what does a circuit designer do, or a schematic designer? Based on the requirement, they do the CMOS design or whatever technology they are designing. Say if it's a digital design, they go with a digital implementation, or for example, a op-amp or something of this sort. They do the circuit designing part. Once this is done, obviously they have to run a simulation to try and see whatever they have designed is working fine or not. Say if it's a digital design, you'll be working with the square waves. If it's an analog design, obviously you'll be having sinusoidal waves. So obviously when a circuit designer is doing these things, it does not have physical information, right? It has got the model parameters of how each and every transistor or resistor behaves. So based on that, they arrive at the conclusion. So once this design is done, so obviously the designer verifies whether the results are met as per the specifications. If no, so obviously the designer tries to use his different techniques or tries to play around with the W by L of the devices or whatever parameters until he or she meets their required results. So once it is met, it goes to the next phase of designing. Say once the design is met, say yes, it goes to the next phase. So what happens in the next phase? So if it's yes, then we go towards the layout design. So what is layout design? Layout design is a physical representation of your schematic. We also call it as analog physical design. Until here, until this stage, everything was in the computer in the form of schematics. From this stage onwards, we move towards the actual physical implementation of the design. So what happens in layout design, right? So assume that a designer has done the schematic of this AND gate. So a layout engineer does the physical implementation of a gate over here. Using this, they build the next hierarchical design. Okay, and assume that this is an analog design, which whatever the schematic designer has done. So obviously layout design techniques, you've got lots and lots of design techniques and concepts based on which a layout engineer does the physical implementation. Now here is a op-amp which has got a current mirror, which has got a differential pair, biasing circuit, and there's resistors over here and cap, whatever. So once this is done, right, the layout design is done. Obviously this has to be verified. It's not just you get a circuit, you do a physical implementation and it's done. It doesn't work like that. So you have to physically verify that. So that is what is the next stage of our design flow. So it's called as physical verification. So what happens in physical verification is we check for two main things, right? Let's take the example of DRC. That's called as a design rule check. So what is design rule check? So now the schematic designer has done his design, he has done his simulation, and the layout designer has done his share of job. Now, the Foundry gives you a set of rule files and tells you that only if you follow these rules and do a physical implementation, we will be able to fabricate your design. So when the layout designer is doing his layouts, he needs to abide by the DRC rules, right? So if he's designing a gate or a digital or analog design, he needs to follow certain set of rules given by the Foundry and verify the design that it's meeting the requirements from the Foundry. That is what is called as design rule check in simple terms. Now it's not just only the fabrication aspects, but there's another part to it called as the layout versus schematic check. This also needs to be done. So what is this? Say whatever the design the schematic engineer has done, that needs to match with the layout, or whatever the layout, the physical implementation, what the layout engineer has done, it has to exactly match with the schematic. That is what we are trying to verify in the layout versus schematic check, right? So once this is done, so here you've got the circuit design, the waveforms are done, the physical implementation is also done. Here, for the sake of simplicity, we are using only two checks, but there are lots and lots of physical verification checks which are done. Okay. Now moving on to the next phase of the design, right? We call it as a parasitic extraction, right? After we implement physically. Now we know that every metal piece, whatever you draw, every device what you draw on the layout design has got some or the other parasitics associated with it. We know that every device, that's a transistor or a resistor or a capacitor, will have something or the other resistance or cap associated with it. Here, if you can see the cross section of this transistor over here, there are so many varieties of cap, right? There is a gate to drain cap, there is a gate to source cap. All of this will be taken into account. Assume that you have done some routing. This is metal 1 and metal 2, and this is the substrate over here. So when parasitic extraction is done, the tool will extract the parasitics of this metal 1 with respect to the substrate, metal 1 to metal 1, that is the sidewall cap, between metal 2 and metal 1, and even with respect to the substrate. So all of the capacitances, coupling capacitances, sidewall capacitances, fringe capacitances, all of this is taken into account, right? Now say, assume you've done a point-to-point connection, right? So obviously there will be a resistance in the metal and the cap associated with it. All of this will be captured in a file called as parasitic extracted file. We call it as a parasitic extracted netlist. So this netlist will have the design information along with the parasitics. So what we do with this file, we back annotate it. Okay. The term used here is back annotation. So what is back annotation? Simulation of a design with its parasitic effects. So note that here what the designer did is a pre-layout simulation without any physical information in it, right? Here we have gone through the physical implementation and verification phase and parasitic extraction. Now you've got a file, you've got the same design with the parasitic information. So then we do the post-layout simulation. So this file is given back to the designer and the designer does the post-layout simulation. So what happens? Then the designer gets the actual results. So here if you assume that this blue color square wave is the pre-layout result, these the other waveforms are the post-layout results with the RC effects in it, right? So this is how the designer gets the information, saying that these are the post-layout results and these are the pre-layout results. Now depending on these results, the designer will tweak around his design again, right? He'll try to verify the design, tweak it again, right? And again, it goes back. Design results have not met. It goes back to the schematic designer. Again, pre-layout simulation is done. Again, the layout designer implements the physical process. And finally, once the whole process is done until the result is met, right? It's a whole iterative process until the required specifications are met. That's when we say the design is complete. So this is the whole process starting from the customer specification till the end. We call it as the analog flow, right? If you have any questions, any queries, please do write into us. Do visit our website. Connect with us on any of these social platforms. Any questions, please feel free to write into us. Now, this is Semiotics for you, creating a path to semiconductor industry. Thank you.